Thank you for being here, for allowing me to speak. This is a project that's very much at the heart of the science I'm doing, of some of the science I'm doing. I have now a group in Stuttgart, and well, it's a whole family now, and it will be impossible to talk about all of them. So we have an extra slot, luckily, later to talk about at least the plotting part of this. Because I don't assume you're a neuroscientist and you know much about EEG or rERPs. First, a primer. So this is what we very typically do in our lab. So we place some electrodes on the head because we're interested in what the brain is doing, and we're measuring brain potentials, right? So this is our voltages, and the EEG. This is what is called the EEG, the electroencephalogram. This is a multiple time series. Do I have a pointer here as well? This is a multivariate time series, so you have each of these electrodes gives you one wiggly line, and as you can see, you cannot see anything, right? This looks like complete noise, and yeah, that's of course a problem. So what are people doing? They are typically using event-based designs. So that means I have a paradigm on the monitor. I show, let's say, a house, and then I record the response of the brain, and then I show a face, I record the response of the brain. So while showing this for, let's say, 300 milliseconds or something like this, I record the EEG. Now I know exactly when I showed these things, right? And this allows me to basically cut the data and just average, and then you get these beautiful pictures here. Each line here is one of these electrodes, one of these sensors, and then you can try to interpret them, measure latencies, amplitudes, etc., and do all your cognitive neuroscience research based on that. Right, and this is what's called the classical ERP, done since 70 years or something like this. Well, it turns out that an average is nothing else than a regression, right? This took this field relatively long to maybe realize. Maybe it's a little bit 10 years earlier or so, the first applications. But people, and me included, have starting to use a regression instead of averaging, right? So basically just replace this step. How that works is, let's say you have here, this is simulated data. You have individual trials for one sensor. Then for each of this trial, you fit a model, like a linear model. You have, in this case, only 2 parameters. You save the 2 parameters, and then you just basically slide it over. You have maybe 1,000 hertz, so you have 1,000 models here for one sensor. And then let's say you have 100 sensors or something like this. That gives you 1,000 times 100 linear models that you have to estimate here, right? So in this case, this is relatively easy. And this is what then is called a regression ERP. And then, of course, you could replace this with much more complex linear models like nonlinear effects, etc. This is all implemented, but I will not further talk about this in this talk. What I'm actually interested in is not this, let's call it the basic regression ERP, but this extension here, because I really want to understand how moving the eyes, and you move the eyes 5 times a second, more often than heartbeats, think about this, but you move the eyes very often, right? So it changes the brain activity quite a lot. And I'm interested in how to even start analyzing this. And with EEG, there are many problems. But one of them is that the brain actually takes longer, like the brain response you get is longer than the distance between eye movements. So that means you have, when you do the eye movements like this, every dashed line here is an eye movement in time. This is what you record. This is actually an overlap of brain activity. And so others and we came up with a way to model this, and this is there I have one illustration, because this overlap clearly completely transforms the shape of the evoked response you get from the brain if you increase the overlap. And so what we're doing from a technical point of view is what's called FIR deconvolution. This is has relation to linear system identification literature, but we need to solve this famous linear system equation, but we have a very large sparse X matrix, so this has 1 million or multiple million entries and has 10,000s of parameters. And this is what we need to solve not once, but 250 times, right? This is a little bit just to get an impression. If somebody is into linear algebra, I'm happy to discuss what kind of stuff you can use to solve this. But it's basically just a bunch of triplets matrices plugged on next to each other, added up. And so to solve this, we developed the Unfold toolbox. It used to be in MATLAB. Well, bad decision in my youth, let's put it like that. And now we are completely switched over to Julia, and we have more than 20 contributors right now. And it's powered by all these really awesome packages. Yeah. We have GPU support, we have iterative solvers, etc. Many things that is really great. This is just a little bit, like if you know stats app, this should look very familiar. You have at some point, you have a fit command, and we use data frames arrays, nothing very special. What I really like, just why I really love Julia, we recently thought, it would be nice to have some complex time series, whether we can do the same thing. Turns out you can just put in complex time series and it just works. And it's like, wow. What the, yeah. Yeah, we were very surprised, but happy surprise. Anyway, so I promised also to show some applications of this. This is work with Anna Gerd. She's interested in face perception, especially when you allow for eye movements. 99.9% of all EEG experiments are at fixation, so you're not allowed to move your eyes, right? And so she was actually interested in whether these results that we find, they generalize. And this is what she found. Basically, you had here the fixation onset. So once you landed on a face or you landed on some other thing in this picture in front of a computer, and we had lots of differences here in the brain response, as you can see. But if you use the magic of unfold, then you can see that this was most of the effects were just overlap effects. So biased overlap, you look at faces first and when you look at a new stimulus, so the stimulus ERP is overlapping, etc. But there's a clear difference here, and this is the difference that you could also find in the literature with the static experiment. So this was a very cool practical demonstration. And much more recently here, we published a little bit of controversial finding where we're looking at decision making. So you get two choices, let's say, I don't know, MATLAB and Python, right? It's a very easy, MATLAB and Julia, and you have to decide which you like better. It's a very easy choice, so you will make a very rapid decision. So you integrate this information, what do I see? And you come to the conclusion very quickly. But then you have maybe a little bit of harder decision. I don't know what's harder than Python and R or something like this. Maybe that's a harder, and then you take more time to accumulate the evidence, basically. And people were modeling this for many years, and they found a signature in the EEG that basically tracked this kind of process. But we show that if you apply this kind of deconvolution models, then this signature kind of goes away, right? So this is just another demonstration that this at least is important to take into account. There's more ongoing discussion whether this is a valid approach or not. Yeah, people who like to do this kind of things, they don't like that it goes away. No, this is a bit mean, but because there are some caveats, but I don't have time to go into this discussion here. By now, well, I started out with Unfold and MATLAB, and right now we have lots of other Unfold toolboxes here. We have Unfold mixed models, Marquee, plotting, simulation, bits. We have everything nicely done in am I already on time? I don't have
30 seconds.
30 seconds, oh geez, okay. I will not be able to go into these, even though I have prepared more cool animations. But these are some of the people involved in this. It is very interesting and challenging to maintain all of these at the same time and keep them synchronized or so. We try to make them as independent as possible. But yeah, I can't talk about this, even though mixed models, awesome package. And there was a post in the morning, and unfortunately, we cannot go back in time. But with this, I will go to the last slide. We are hiring. If you're looking for a PhD position, this sounds exciting, please contact me. And we also have a permanent position in science. So if this sounds interesting, well, also contact me, I guess. And yeah, thank you.
Okay, any question? Please, a question. I don't have any clever question for.
So just because you were teasing it at the end of part 2 that you don't have any time to go into the details of the conflict, maybe you can say a few words about it or what's going on there?
Well, it's a complicated story, basically. They show that with very simplified data, that this kind of deconvolution approach, it breaks down, and it just basically, you have a parameter explosion because there's not enough, it's not unique, there's no unique solution, and you get artifacts. But the model they choose as the simplified model, they never ever would use in any other of their analysis that they're typically doing. So this is kind of the conflict, and it's a special, like, we're still analyzing exactly in what regime our model works and what it doesn't work in. Thanks.